Hi everyone. So we're going to look at trigonometric substitution in this video. Before we do that, I just want to remind you of the derivatives of inverse trig functions. So the derivative of the arcsine being 1 over the square root of 1 minus x squared, derivative of the cosine -1 over the square root of 1 minus x squared, and arctangent has a derivative of 1 over 1 plus x squared. So what we see is that these transcendental functions have derivatives that are algebraic. So they have rational and radical components to them. So when we see functions with structures similar to these that we are trying to integrate, often we're going to end up with a trig, usually an inverse trig function, as our antiderivative. But that's not always easy to see right off the bat. And the structures don't always look quite like this. I mean, we could have something that looks something like an arctangent, but maybe it's just an irreducible quadratic. In other words, one that can't be factored, as an example. Well, that's not quite the arctangent, but I can't factor it, so I can't use partial fractions. And we actually can manipulate it a little to turn it into more of an arctangent. And they don't even have to be fractions. So if I have something like the square root of, I believe this is one we're going to do a little later, 4 minus x squared, if I'm trying to integrate this one. It doesn't quite have that same structure, but I will direct you maybe to go back and look at when we developed those derivatives, how they came about. We see a lot of these same things. It's essentially a Pythagorean kind of structure because I have something squared minus something squared. And so those sorts of things are going to show up a bunch, and there a trig substitution is helpful. So we're going to look at a couple of different scenarios. The first one that I just talked about a moment ago, where it's sort of an arctangent scenario, and we are in fact going to end up with an arctangent, but it doesn't immediately look that way. So when I look at the integral of 1 over x squared plus 2x plus 5, it immediately suggests to me partial fractions. But when I try to factor this denominator, I find that it is in fact unfactorable. So an irreducible quadratic. So I'm not going to be able to break it up into two smaller fractions. I also can't do a straight up u substitution because the derivative of x squared plus 2x plus 5 is 2x plus 1, or 2x plus 2, sorry, and that 2x plus 2 doesn't show up anywhere else in here. So what I'm going to do to try and make it more like that arctangent form, in that arctangent form I have x squared plus a constant. That extra linear term in the middle is somewhat problematic. So I don't want that. I want something squared plus a constant. Well, that's completing the square. So when I end up with a quadratic that's unfactorable, I'm going to complete the square. And that's going to allow me to get that sort of Pythagorean structure that I'm looking for. So I have x squared plus 2x plus 1 would be a square. But I have plus 5, so in other words, that's an extra plus 4 here. This is my perfect square, so I have x plus 1 squared plus 4. Now this is getting me closer to that arctangent form. So I have x plus 1 squared plus 4 dx, but the problem is I still have that 4. And I don't really want to have to deal with that 4. I should have a 1. Well, what I'm going to do is I'm actually going to say, okay, it looks very strongly like an arctangent form. So I am going to replace my variable in here with something involving tangent. So essentially the substitution that I'm going to do is I'm going to take this expression that is being squared, my expression in x, and I want that to instead be the tangent of something squared. So in other words, I'm going to replace x plus 1 with the tangent of theta. That's the substitution. Oh, no, sorry. That is not the substitution I want to do because I have that 4. That 4 is the problem. The 4 is what I want. So I want this to actually be 2 tan squared because I want this to be 4 times tan squared of theta plus 4, which allows me to factor out the 4. So I'm wanting to have a coefficient of 4 so that I can factor it out. So I need a 2 here. So I'm replacing, the substitution I'm doing is x plus 1 is being replaced with 2 tan theta. In order to figure out what replacement this is going to have for the dx, well, I derive both sides. So the 1 doesn't matter, so I get a dx equals 2 secant squared d theta. So that's the substitution I'm going to do. I'm going to replace x plus 1 with 2 tan theta, which now gives me 1 over 4 tan squared theta plus 4. And I'm going to replace dx with 2 times the secant squared. Oh, forgot to missed a theta in there. So 2 times the secant squared of theta d theta. So now I end up with something that is trigonometric in nature. It's not what I started with. And initially that doesn't seem like it's gotten me anywhere. I mean, it simplified the coefficient a little, but it does because with trig I have a lot of identities, so I can do some substitutions and so on in there. So what I'm going to do here, I'm going to factor out the coefficient, so it's 1/2, it's 2 over 4, secant squared theta over tan squared theta plus 1, d theta. But when I see secant and tangent in the same expression, I think, well, that's actually really useful because I have an identity that connects the two of them. In fact, I have an identity that tells me that tan squared theta plus 1 is actually equal to secant squared of theta. So in this case, that's the best case scenario because that cancels completely. So I have 1/2 times the integral of 1 d theta, which is just theta over 2 plus c. Well, that's great. I have my integral. Almost. We're not quite there yet because I have this in terms of theta, and theta is just a tool I introduced into this question. So now I have to go figure out how do I replace theta with something involving x. So now I'm going back to my original substitution. Well, if I start trying to isolate theta, I get x plus 1 over 2 equals tan theta, which means that theta is equal to the arctan of x plus 1 over 2. Well, that's where our arctangent comes in. So now I know that the integral is equal to 1/2 times the arctan of x plus 1 over 2 plus c. That's the antiderivative I was looking for. So the technique basically is to say, now in our u substitutions, we were wanting to always substitute like an interior function in some sort of chain rule scenario. But here, this is something quite different. Here we're introducing trigonometric functions because we're hoping essentially to be able to use one of those Pythagorean identities to simplify something down. So I have a number of different identities, one that connects sine and cos, one that connects tangent and secant, and one that connects cosecant and cotangent as far as Pythagorean identities go. And those things are also related in terms of their derivatives. So sine and cosine have derivatives that are each other basically. Tangent and secant are in each other's derivatives, and cotangent and cosecant are in each other's derivatives. So there's a connection there. So if I have, essentially I'm looking for a Pythagorean kind of structure, the sum of two squares or the difference of two squares or the square root of the difference of two squares, these sorts of structures. And then I'm trying to turn that into one of those Pythagorean trig identities. So that's what we've done here. I've looked at this, I've said, I'm going to complete the square, so it takes on that sum of two squares format. Now here I took some pity on you, and it was x plus 1 squared plus 4, which was a perfect square. But even if it isn't a perfect square, it's still the square of something. If that was a 7, it's still the square of the square root of 7. So we're creating those squares, and that's what we're after. So let's look at another example where it's not directly, like it's got that constant minus x squared under a square root. It's not 1 over that, so it's not just going to be a direct arcsine or arc cosine, but it still is something that is, I'm going to keep referring to it as a Pythagorean structure. So essentially what I'm looking at when I look at this is I am trying to get this to take on the form of 4 times something. So first off, I'm going to want a 4 as a coefficient. So I want this to become 4 times. Now, for simplicity's sake, and I could in theory do this with any of my Pythagorean identities, but 1 minus sine squared equals cos squared, or 1 minus cos squared equals sine squared. So I can make this 4 cos squared or 4 sine squared. Doesn't really matter which. I like to use sine because its derivative is positive, so it messes with the negative signs a little less. So I'm going to replace it. Essentially, I'm going to want to replace x squared with 4 sine squared so that I end up with, so the square root of 4 minus 4 sine squared is going to be the square root of 4 cos squared theta, which would then allow me to get rid of the square root and just have 2 cos theta. So that's the process I'm trying to create here. I'm trying to create that Pythagorean identity so that I can express a binomial as just a monomial, and in fact a perfect square, so I can take the square root. That's the intention. So then I ask myself, what substitution do I have to do to make that happen? Well, in order to make that happen, x has to be replaced with 2 sine theta, which means that dx has to be replaced with 2 cos theta d theta. So that just, again, this taking the derivative is why I chose to make it 4 sine squared theta instead of 4 cos squared theta, is just because then I don't have to worry about a negative sign when I take the derivative. But the process would work the same. You could definitely use cosine instead of sine. Your end result will look a little different, but it will be mathematically equivalent with potentially a constant difference. All right, so this is what I have. So let's replace that in the integral. So I've got the square root of 4 minus x squared, I can see has already simplified down. I've already written all those steps. It would be 4 minus 4 sine squared theta, which is 4 cos squared theta, which becomes 2 cos theta. That's coming from here. And then dx is being replaced with 2 cos theta d theta. So now, so that's coming from here. So now I've got 4 times the integral of cos squared theta d theta. Oh, but how do I antiderive a square, a power of cosine, when I don't have its derivative here? I don't have a sign in there to let me do a substitution. Well, here's where more identities come in, and this is a common one you'll see a lot. If you're having to take the antiderivative of an even power of sine or cosine, you're going to use a double angle identity for cosine. Because if I recall here, the cosine of 2 theta is equal to 2 cos squared theta minus 1. It also can be written as 1 minus 2 sine squared theta, which is why cos 2 theta is going to show up whether we have a sine squared or a cos squared. But this is it's cos squared that interests me now. So if I isolate cos squared, I get cos 2 theta plus 1 all over 2 equals cos squared theta. So this is what I'm going to substitute in to my integral. So now, well, I have a 4 as a coefficient, so that 4 will cancel with the 1/2, so I'll end up with 2 times the antiderivative of cos 2 theta plus 1 d theta. Well, now this is something I can integrate. The cosine of 2 theta has an antiderivative of the sine of 2 theta, so I've got 2 times sine of 2 theta, but divided by 2 to make the coefficient work out. And then 1 has an antiderivative of theta plus some constant. So in other words, sine 2 theta plus 2 theta plus c. Okay, so we have our antiderivative. The last thing we have to figure out is how can I re-express this as a function of x? Sine 2 theta is a tricky one because I don't have 2 theta. So for that, I'm going to use the identity that this is 2 sine theta cos theta. The 2 sine theta part's easy. That's x. That was my actual initial substitution. But cos theta, I'm going to have to think about. So I'm going to look at a triangle. I'm going to say, let's let that angle equal theta, for example. So what I have here is that sine theta equals x over 2, which if I let this opposite side be x and the hypotenuse be 2, means that the adjacent side would be 4 minus x squared. Well, hey, that's what I started with. That was my initial expression. So that is a good indication that I'm on the right path, which means that the cosine of theta is the square root of 4 minus x squared over 2. It shouldn't be surprising that that same square root is going to show up in my antiderivative, because when we do take a square root function, a derivative of a square root function, we usually end up with that same square root somewhere in there. So substituting here, what I have, sine of 2 theta is equal to 2 sine theta, which is x, times the cosine of theta, which is the square root of 4 minus x squared over 2, and then plus 2 theta. Well, theta is going to have to be the arcsine of x over 2. Oops. So the arcsine of x over 2, but I've got a 2 as a coefficient, so this gives me 2 times the arcsine of x over 2, and of course plus c. So there is my antiderivative. A non-trivial amount of work. There's a lot going on here, so feel free to watch that again and pause and think about it at various stages. But just to kind of quickly recap, I looked at this, I thought, ooh, that has kind of a Pythagorean-ish look to it. It's the sort of thing that shows up when I'm doing the Pythagorean theorem. And in fact, we did see it show up when we were doing the Pythagorean theorem over here in the triangle that I've drawn in red. So what I'm trying to do is I'm trying to use that sine squared plus cos squared equals 1 identity, but I don't need it to equal 1, I actually need it to equal 4. So I have 4 minus 4 sine squared. That's what I'm trying to create. So I want to replace x squared with 4 sine squared, which means I'm substituting x for 2 sine theta. When I do that, the square root of 4 minus 4 sine squared theta, I can use the identity to turn it into the square root of 4 cos squared theta, which is just 2 cos theta. And I then replace dx with 2 cos theta d theta, so that's where I ended up. Now when I'm looking to integrate an even power of cosine or sine, so generally cos squared theta or sine squared theta, this is where I use the cos 2 theta identity, so you can see that in green here. And from there I integrated. And once I had my integral expressed as a function of theta, I had to figure out, using trig identities and using the Pythagorean theorem, how to re-express it as a function of x, and that's where I finally ended up. We're going to look at one more example of this together, where the numbers aren't quite as nice, but at least they're still perfect squares. This still works even if the numbers are not perfect squares, you just end up with coefficients that are irrational numbers. All right, so this one a little more complex, but again, none of my usual techniques would work, because if I were to try and do a basic substitution of 25x squared minus 4 equals u, then du is going to be 50x, and I do have an x here, but that x is in a denominator, so that's not helpful. It's the wrong power, basically. It's x to the negative 1. But I see inside the square root a bit of a Pythagorean structure. So let's think about how we can deal with this. Now, the identity that I'm trying to use, I have, in the previous case, I had a constant minus a variable squared, so I was using the identity for sine and cos because that has the constant minus sine squared or the constant minus cos squared. But here I have the identity where I have a ratio minus a constant. So the identity that I'm going to use here, and this is not the only one you could use, but it is one that often works. So secant and tan, because I have the identity that says that tan squared theta equals secant squared theta minus 1. So what I'm trying to create here then, I don't have minus 1, I have minus 4. So I'm going to try and create 4 secant squared theta minus 4. That's what I'm trying to create, so that I can substitute that with 4 tan squared theta. And then I can take the square root of that. So that's what I'm after here, trying to create that. So what I need this 4 secant squared theta to equal 25x squared. So that is my substitution. I'm substituting 25x squared with 4 secant squared of theta. In order to figure out what I would replace dx with, I'm going to take the square root of this. So I get 5x equals 2 secant theta, which means x is being replaced with 2/5 secant theta. That's helpful because I do have x in the denominator, so I'm going to have to replace that as well. So this 4 tan squared theta, I'm going to be able to put inside the square root here, and 2/5 secant theta, I'm going to be able to put in the denominator. And then dx is equal to 2/5. Derivative of secant theta is secant theta tan theta d theta. So that is being replaced with the dx. This does not seem like it's making things simpler, and often with integrals, it's not so much about making it easier as making it possible. The form I currently have it in, there's really nothing I can do with, so I have to manipulate it into a form that I can do something with. All right, so now my integral is the square root of 4 tan squared theta, so in other words, 2 tan theta, over 2/5 secant of theta times 2/5 secant theta tan theta d theta. Okay, well, right away it gets better because stuff cancels. So now what I have is 2 times the integral of tan squared theta d theta. Okay, well, this is better, and there's a few different ways to go about this one. What I'm going to do is I'm actually going to resubstitute in tan squared theta is secant squared theta minus 1. The reason I'm going to do that is secant squared theta is something I know how to antiderive, something I know how to integrate. So I'm going to turn this into 2 times the integral of secant squared theta minus 1 d theta, because the antiderivative of secant squared theta is tan. So I've got 2 tan theta minus 2 theta plus c. So now I have my integral. Not quite done. One of the things about integration that makes it kind of annoying is you want to just get the integral and be done, but we're not. We have to get it back as a function of x. So going back, well, the easy one is going to be the theta, because if I expressed x equals 2/5 secant theta, then that means 5x over 2 equals secant theta. I'm actually going to write this as a cosine. So the cosine of theta, because I don't really want to use arcsecant. So the cosine of theta equals 2 over 5x. Theta equals the arccos of 2 over 5x. So that's the first part. We didn't do those derivatives, but essentially, if you were to do the derivative of arcsecant, you're going to end up with a square root in the numerator. So that's why these have kind of shown up. And then the other thing I need is the tangent of theta. Well, I defined secant theta as 5x over 2, so I'm going to draw my triangle. And if this is theta, secant is hypotenuse over adjacent, so 5x for the hypotenuse, 2 for the adjacent. The opposite side, therefore, has to be 25x squared minus 4, the square root of 25x squared minus 4, which, hey, no big surprise there. We end up with our original radical. So then the tangent of theta, well, opposite over adjacent, so square root of 25x squared minus 4 all over 2. All right, so now I can substitute this back in. 2 times the tangent of theta, well, the 2 is going to cancel with the 2 in the denominator. So 2 times the tangent of theta is 25x squared minus 4. And then minus 2 times the arccos of 2 over 5x. And then plus c. So there is the antiderivative that we are looking for. For practice, in the read book, these types of things are in section 18.2 of the book. If you want more practice with using trig identities to manipulate trigonometric integrals so that you can integrate them, that's in section 18.1. But proper trig substitution, that's in 18.2. That's when we take something that doesn't have trigonometric ratios in it and we introduce trigonometric ratios in order to make it integrable. And in Stewart, that's section 11.5. Stewart also does have practice for the using trig identities to manipulate ahead of time. I mean, something that already is trigonometric, but they actually do that in section 11.5. They kind of mix it all in together and call it all trig substitution. It's not properly correct. So trig substitution is when you take something that isn't trigonometric and you bring in trig ratios. Manipulating something that already is trigonometric using trig identities is just algebraic manipulation of that statement.